All right, you guys. So I'm trying to work with this video stuff. I hope it's successful. So we're going to study now the product of series. And I'm going to just remind you that if we have series A, which is the sum of n from 0 to infinity, and we have another series B, which is the sum of Bn, n goes from 0 to infinity. Then we define the sum of the series. So this is definition. That the sum of the series uh, is defined as C, which is the sum of Cn, where Cn equals to An plus Bn. I know mathematicians are a little bit anal retentive, but there is a little bit of a point to it. The sum of An, n from 0 to infinity, plus the sum of Bn, n from 0 to infinity, is not really the sum of the series because these are not the series. So these are the series and these are not. Okay. And in the last lecture, I proved that if the series A converges and the series B converges, then the series A plus B, as defined here, also converges. And it converges to the right thing. Well, what do I mean by the right thing? By the right thing, I mean it converges to the sum of the series. Good. Now we're all together on it. Okay, now we're going to do something very, very similar. And now I want to do the same thing with the product of the series. And I will remind you the definition of a product of the series. And the product of the series was defined to be, so this is the same series A and B as defined above. And the product of the series is the series C, which is equal to the sum of Cn, n from 0 to infinity. Only this time Cn were defined to be the sum of Ak, Bn minus k, k from 0 to n. So in here, I have a finite sum. These are well-defined numbers. And then I'm taking the infinite sum of all those numbers. Remember what it was like. It was like A naught Bn plus A1 Bn minus 1 plus A2 Bn minus 2 plus etc. plus A and B naught. Okay, so that's the way we define the sum of the series, and I strongly, strongly, strongly recommend you that you review the way and the reason we defined it this way because it's a beautiful definition. It is called the Cauchy product, and it's very, very, very clever and has a lot to do with multiplication of polynomials. So I do recommend you look into it very, very seriously. Okay, so what do we want to do now? We're going to assume that A and B converges. And ask a natural question, what about A times B? A times B. Do these series converge? And if yes, then do they converge to the right thing? What does the right thing means? The right thing means that it converges to the product of A times B. And There are partial answers to that question that we're going to discuss now. One of them we're not going to discuss. Rudin doesn't discuss it, so I'm not going to discuss it later either. But somewhere in intermediate analysis 2, somewhere at the very, very end, you will see that there is a theorem that if the series converge, then it converges to the right thing. That is, they converge to the product of the series. However, as I'm going to show you next, A and B may converge, but A times B, as defined using this Cauchy product, does not converge. Okay, so let's deal with an example. And here is an example. I'm trying to see if you can see me. So again, I have A, which is a sum of AN, and B, which is a sum of BN, and then I have C, which is a sum of Cn, where Cn is equal to the sum, it's a finite sum, k from 0 to n of ak bn minus k. And what I'm going to do together with Rudin is I'm going to take my a to be the series sum of minus 1 to the power n times 1 over square root of n plus 1. So this will be the series of the form 1 minus 1 over square root of 2 plus 1 over square root of 3 minus 1 over square root of 4 plus etc. Now, most of the proofs that I'm going to do here are really not difficult, but it really helps not to rely completely on the sigma notation and to actually see what series we're dealing with. So my B will be the same as A. Okay, and what I'm going to do is I'm going to try to multiply A by A and see what's going to happen. So if I'm multiplying A by A, I will have the series that look like this. So A times A will give me the series Ck Cn, and from 0 to infinity, where my Cn is equal to the sum of A, K, A, n minus K, K from 0 to n. And let's see what that gives me. That gives me, so AK, I will have minus 1 to the power K times 1 over square root of K plus 1. Agree? This is my Kn. And then I have to multiply it by minus 1 to the power n minus K, 1 over square root of n minus K plus 1. Now let's deal with this minus 1s first, because notice that minus 1 to the power k times minus 1 to the power n minus k is equal to minus 1 to the power n. And then I will have 1 over square root of k plus 1 times 1 over square root of n minus k plus 1. And notice that this minus 1 depends not on k but on n. In other words, it is the same for all k, and I can just pull it out of the bracket here. This is equal to the minus 1 to the power n times the sum of 1 over square root of k plus 1 times 1 over square root of n minus k plus 1. Okay, what I'm going to do now is something a little bit different from what Rudin is doing. I think it is easier that way, but you tell me. Okay, so now the Cn in absolute value is equal to the sum of 1 over square root of k plus 1 times 1 over square root of n minus k plus 1. Are we good? Okay. Now notice that k plus 1 is definitely less or equal than n plus 1 because k is less than n. Here k goes from 0 to n. And therefore, this quantity is greater or equal than 1 over square root of n plus 1. Now, n minus k plus 1 is also less or equal than n plus 1. And so this quantity with reciprocals taken is also being greater or equal than 1 over square root of n plus 1. Okay. So what we get as a result of it is the following, that Cn is greater or equal than the sum of 1 over square root of n plus 1 times 1 over square root of n plus 1. Here k goes from 0 to n, which is equal to the sum of 1 over n plus 1, where k goes from 0 to n. Now, this number over here, 1 over n plus 1, has absolutely nothing to do with k. In other words, like if I sum, I don't know, 3, and k goes from 0 to n, then I will have 3 times 3 times 3, n plus 1 times. And so all I will get as a result of it, I'm trying to make sure that you can see it, is 3 times n plus 1. Okay, so similarly in here, when I'm adding those terms which have nothing to do with k, I'm just taking this number and add it to itself n plus 1 times. And so as a result, this quantity is equal to the sum of n plus 1 times, not the sum, n plus 1 times 1 over n plus 1, which is equal to 1. So the conclusion is that the absolute value of the term Cn are equal, greater or equal than 1, and in particular, the term Cn do not converge to 0. And we know the theorem that says that if the term of the series do not converge to 0, that will mean that the series Cn diverges. And that's the end of a counterexample. Okay. Good. So we saw here that it is possible that the series converges, but the product of those series diverges. However, and this is where something comes to rescue. However, there is another problem, and that is if A, once again, equal to the series an, n from 0 to infinity, B equals to the series bn, n from 0 to infinity. Okay, you can see it now. And once again, I'm going to take the series C, which is equal to the sum of Cn, where Cn equal to the sum ak bn minus k, k from 0 to n. So there is a next theorem that says that things are not as bad as we may imagine they would be, because it turns out that if one of the series, for instance, if the series A not just converges, but converges absolutely, which means that the series an with absolute value, and from 0 to infinity converges, well then, if B converges, and converges absolutely or not, I really don't care. In that case, the series C over here converges and converges to the right thing. Again, what's the right thing? It means that it's okay. It means that this video is a little bit different from what I'm used to, and so the letters appear differently, and sometimes I'm lost in what I'm writing, so I apologize. So let's try to do the proof of this theorem. And again, the proof is not very difficult, but it requires a lot of tedious writing. The rest of it is basically high school thing. So I'm going to use, again, an to be equal to the partial sum of the series a. This is k from 0 to n. of AK, and Bn will be the partial sum of the series Bk, k from 0 to n, and finally Cn will be the partial sum of the series uh, over here with this particular definition. Okay, so what I would like to do is I would like to do a little bit of computation, and I'll say that, well, what is C0? C0 is equal to A naught B naught, agree? And C1 is equal to A naught B1 plus A1 B naught. And C2 is equal to A naught B2 plus A1 B1 plus A2 B naught, etc. The nth term here, Cn, will be equal to A naught Bn plus A1 Bn minus 1. I hope you follow me. Plus A2 Bn minus 2 plus etc. all the way to An B0. Okay, so if I want to find the partial sums, the capital Cn, this will be the sum of those guys. And I'm going to add it in a very, very particular pattern. So first I'm going to add all the terms with A naught, and I will have A naught times B naught plus B1 plus B2 plus etc. plus Bn. And then I'm going to add all the terms with A1. So in the second column, I will have plus A1 times B naught plus B1 plus etc. plus Bn minus 1. And so I will go on like this until I'm going to add the last term, and the last term will simply be A naught An B0. Are you good with that? Okay, so that wasn't very difficult. It's just a distributive law. Okay, so let's see. This is equal to A naught times Bn. This is over here a partial sums, nth partial sums of the series B. And then I will have plus A1 times Bn minus 1 plus etc. plus An times B naught, which is really just little b naught, but it's still a zeros partial sum of the series B. And now, together with Rudin, I'm going to introduce one extra notation. And so let's suppose that Bn minus B, let me call those numbers beta n, okay, just for fun, just for abbreviation. So in that case, the sum, so in this case, B, maybe I should do it another way around, just to follow Rudin. I'm trying to think. Yeah, Bn is equal to beta n plus B. So this is A naught B plus beta n plus A1 times B plus beta n minus 1 plus etc. plus An B plus beta 0, right? Nothing difficult here, just a little bit of a lengthy formulas, but everything else is trivial. And so this is equal to A naught plus A1 plus etc. plus An times B plus A naught beta n plus A1 beta n minus 1 plus etc. plus An beta naught. Okay, so this here is the nth partial sum of the series A. So this is A and B, and then I'm going to add to it, a gamma, which is this gamma over here is being equal to this A naught beta n plus A1 beta n minus 1 plus etc. plus An beta 0. Now, again, these are long computations, and to be honest with you, I like it probably as much as you do, but they're not difficult. You just have to kind of write it down yourself and see that all I'm doing is a little bit of a distributive law. So I know that An converges to A, right, because the series A converges, which means that this A and B converges to AB. Oh, this is gamma n. And so all I have to do All that's left for me to do is to say that gamma n equals to a naught beta n plus a1 beta n minus 1 plus etc. plus a n, oops, beta 0, that this gamma n converges to 0, right? And if I prove that, then I'm done with the theorem. Okay, so I'm going to switch to the next page and I'm going to rewrite what's written in this page. I have this gamma n, which is equal to a naught beta n plus a1 beta n minus 1 plus etc. plus a n beta 0, where beta k is equal to, what were they equal to? It's equal to bk minus b, and that thing converges to 0 because I assume that beta k, this is a partial sums for the series B, and this partial sums converges to the series B. So I hope you're good so far, and I'm going to rewrite this particular thing in an opposite way. I apologize for doing that, but this is unfortunately somewhat necessary. I'm going to write them down from right to left. So I'm going to say that gamma n, this is equal to beta naught a n plus beta 1 a n minus 1 plus etc. plus beta n a 0. Okay. Okay. And now comes the trick. This trick is not really difficult. It is not really anything but I need to introduce an extra parameter. You see, if I look at this, I know that like beta n converges to 0, right? Because this is a difference between uh, beta n and b, and so it converges to 0. So if little n is very, very large, then definitely beta n converges to 0, and they can disregard it. And if these are not very large, then an minus 1, etc., they converge to the right thing. And so here is the trick, and this is a very clever trick, not a difficult trick, but clever trick. So we know that beta n converges to 0, which means that for any epsilon greater than 0 that I'm going to fix an epsilon, there exists a number capital N such that if little n is greater than capital N, then uh, beta n is less than epsilon. Okay, and now I'm going to replace my gamma n by the following thing. It will be equal to, well, it's equal to beta naught a n plus beta 1 a n minus 1, and I'm going to add it not to the whole end. I'm going to stop in the middle, and I will say that this is beta capital N a, what will be the a, n minus little n, and then I'm going to write plus, well, plus whatever is left here, and what's left is beta n plus 1 a n minus n plus minus 1, and I will go on like that all the way to the end, which is beta n a naught. Okay, so this is equal to this quantity, and therefore it is less or equal than the sum of these two absolute values, and this particular thing is nothing but triangle inequality for absolute values of the real numbers. Okay, so now I'm going to keep n fixed. N is fixed once and for all. And if n is fixed once and for all, I'm going to say that this is less or equal, this gamma n is less or equal than this beta naught a n plus, ooh, this was beta 1, plus beta 1 an minus 1 plus etc. plus beta n an minus n, right? This is this term over here that I'm not really changing. And what about this term? Well, this term will be the maximum. So this is less or equal. This thing is less or equal, this particular part, then the maximum of those beta k, and here k will be greater than n, right? The coefficient in front of betas are all greater than n. And then what do you have? You have the sum of n minus 1 plus a with absolute value plus an minus n minus 2 plus etc. Again with absolute value. A naught. Let me rewrite it because I kind of written it very, very badly. So I will say that gamma n is less or equal than this beta naught an plus beta 1 an minus 1 uh, plus etc. plus beta n an minus n. And so for the second part, I'm going to factor out the maximum of those numbers beta n, uh, those beta k, where k is greater than n. That's essential, right? And what I will be left with is the sum of j from 0 to n minus 1 with absolute value. Okay, here comes a trick, and this is where absolute convergence was needed. These are the partial sums of the series A. And these partial sums, because the series converge absolutely, the partial sums are bounded by some number, let's call it alpha. This number is fixed once and for all. All the partial sums of the series are bounded by some number, and this one is less or equal than epsilon. So what I have is that gamma n is less or equal than beta naught an plus etc. beta n an minus n plus epsilon times alpha. Okay, and so here is the trick. The trick is that now I'm going to let n tend to infinity. Well, if n tends to infinity, this is a finite sum. Little n tends to infinity, but the capital N is fixed. So if this is a finite sum, then all a's tend to 0. Remember, the series with ak converges, so the terms tend to 0, and there are only finitely many of them. So this quantity tends to 0, and so my conclusion is that the limit, or to be more appropriate to say, that the lim sup of gamma n. So this tends to 0. It will be less than epsilon times alpha. And epsilon and alpha have absolutely nothing to do with n. And therefore, this is true for all epsilon. And that implies that the lim sup of gamma n is equal to 0, which implies that the limit of gamma n equals to 0. And remember, this is exactly what we were trying to prove at the very, very beginning. So this is a proof of this theorem. It is not too difficult, I hope. It's a little bit lengthy. And the only clever trick here is introducing this number capital N in a very, very, very proper way. And once we do that, keep capital N fixed, so that's epsilon n fixed, and then you let little n go to infinity, and then that will do the job. Okay, so I hope you read it. I hope you understand it. And if there are some problems, ask me questions. And this will be the end of the first part of this lecture.